All right, back. Here we are on free response problem number 3. We're dealing with, let's see here, we're dealing with oxygen, which is O2, and ozone, which is O3, a very common question asked on the test. So draw the Lewis structure for O2. You end up with this. And draw the Lewis structure for O3. Hello, little friend. Bye-bye. Yeah, for O3, you're going to end up with, after doing your shifting, you're going to end up with something that looks like that, and we have a possible resonance structure for that, so we're going to have to show that. Okay. Is the OO bond length shorter in oxygen or ozone? Okay. Oxygen, the double bond is spread out over both sides of O3, thus making bonds longer. So if you notice, this double bond here is sometimes here and it's sometimes here, whereas in O2 it's localized right there. So this bond length is going to be like that, whereas the bond length for O3 might be a little bit longer because that double bond is not always there. So it's also going to have a smaller bond energy. Okay, so in O2 we have, let's see a little chart, and in O3, always drawing the resonance, sigma pi, we're going to have 1 sigma, 1 pi. In this we're going to have 2 sigma, 1 pi. 2 in the resonance structures as well. What's the hybridization of the central atom? Okay, sp, p. So it's sp2. There's 3 things around it. Any difference in polarity between O2 and O3? Yes. O2 is nonpolar. O3 polar. Lone pairs on O3 central oxygen create an asymmetric shape. Okay, let's revisit that. If you look at the structure, these lone pairs right here can form the bond and push it down. Alright, so number 4. Please complete and balance each reaction below. Answer the associated question. So in the first reaction, it says a solution of ammonium chloride, so it's a water word. So NH4 plus Cl minus reacts with a solution of sodium hydroxide, Na plus OH minus. Okay, we see ions everywhere, so we're going to swap, and cancel alkali metals. So there's our stick right there. NH4 plus OH minus is going to produce NH3 and H2O. Draw a Lewis structure for NH4 plus. Okay, so that plus means there's one less electron. So we got N, we have H, we have H, we have H, we have H. We're going to connect, and we're going to lose this electron and connect there, and we're going to end up with a tetrahedral sp3 nonpolar substance that all has a positive 1. We show that charge at the top, and we put polyatomic Lewis structures in brackets. Concentrated hydrochloric acid, water word, H plus Cl minus, reacts with dilute sodium carbonate, another water word, Na plus CO3 2 minus. We have swaps. We cancel the alkali metal. H plus and CO3 2 minus make our old friend H2O plus CO2. Don't forget to balance with the 2 there. Draw Lewis structures for CO3 2 minus. This means 2 less electrons. So we have C, we have O, we have O, and we have O, dot, 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 dot. 2 available to bond, 2 available to bond, 2 available to bond. It's got these pairs left over. Let's make sure we put those. Okay, so here we go. We're going to connect and go for it. So, I'm going to go up there, I'm going to go up there. Okay, I'm going to go for this. I'm not going to go for that because then I won't be able to go for this. Go here, and I'm going to fill in those extra. What's going on here? Extra electrons. So my Lewis structure is going to look like this. And I can have 3 different resonance structures for that. Double bond in 3 different locations. There it is. Calcium is burned in air. So calcium, oxygen, we get 0, 0. So someone's going to have to go up. Calcium's going to go up. Someone's going to have to go down. They're going to stick together, and we're going to balance. Thanks. Is calcium's radius larger on the reactant side or the product side? Well, on the reactant side, it's like this, and on the product side, it's like this. So it's larger on the reactant side. And it's larger on the reactant side. More electrons, more shielding. All right, guys, take care.